Okay, so our first example here in section 5.1, just to step back a little bit, if you did the birthday problem ed puzzle, you'll notice that we moved into a much more advanced probability model, but just explored it using the concept of simulation. So before we continue to do more theoretical probability, we're going to look at this concept of simulation because it's very, very powerful. So let's look at the first example of whose book is this. So what's happening here is we have 4 students. And what's interesting about this particular problem is it's very, very similar to the Pollyanna problem that I explained in my birthday problem ed puzzle, where we want to know what's the probability that somebody gets their own name in a Pollyanna. Now, the situation that I am exploring with a former student of mine who's now an actuary, so the two of us enjoy these things, we're looking at a situation where we have 6 people. In this situation here, you only have 4, so it's a little bit easier for us to analyze, and my student and I were able to do that, and we did correctly calculate that 0.375 number that you see here. He and I could show you why that is correct, which again is a little bit more advanced from where we are right now, but that's okay. We'll take their word for it. So what we're doing here, though, is a simulation, right? They do 20 trials, okay, where we just say, like, let's run through this situation and see out of 20 times how often does somebody pick their own book or pick their own name out of a Pollyanna hat. And you can see in 20 trials, in the first couple of trials, we see a lot of variability here, right? We're moving around. We know this is the true value, 0.375. Okay, but as we continue on and do more and more trials, we get really, really close with the simulation, right? Not any actual calculations, but just with the simulation, we start to get closer to the true theoretical value, which we know is 0.375. Even more powerful, and this is what we call the law of large numbers, when we do this 500 times, if we can do something many, many times, then we get really, really close to that theoretical probability. I like to explain it like this. If I tossed a coin 10 times, it would not be unusual to get heads 8 times. That could happen, and we could talk about the theoretical probability of that. But if I toss the coin 100 times, it's going to be much less likely to get 80 out of 100, right? Both of those are a percentage of 0.8 or 80%. And then if I toss it 1,000 times and get 800 heads, those things are going to become more and more unlikely. What becomes more likely with a larger sample size or a larger number of trials is the theoretical probability. This is what we call the law of large numbers, and this is what we mean by probability. Probability, the basic definition is simply what happens, what are the outcomes in many, many trials of a situation, of an event. When we toss a coin, a lot of times people misinterpret what probability means. They toss a coin 3 times and they get heads all 3 times, and they say, well, the next toss should be tails because it should be 50-50. That's an incorrect understanding of probability. And the birthday problem is a great example of where our intuition, when we think that way, it fails us. So here's a great example of probability applied in the business world. And we, for sure, insurance companies make lots and lots of money. If you're a sports fan like me, every other commercial is, Geico or USAA, or I'm blanking on the car insurance one, where they have the guy from 24. It's Allstate, right? Allstate, the discount driver, the safe driver discount. These are all insurance companies. They're on TV all the time, paying lots of money for these commercials because they make lots of money. And how do they do it? They do things like what we have here. If we knew everybody that's going to break their cell phone or everybody's going to get in a car accident, then, we would only charge those people. Somebody that's, been driving for 30, 40 years and never had a car accident, why should you charge them anything for their insurance, right? They have no need to pay them. So what they do is they know that 1 in every 20, they know the probability that somebody's going to get in an accident, and that's not, it's different for every person. So, and a lot of you could probably relate to this, what you find out, like you get these discounts if you're on the honor roll. Why? It's not a causal situation. It doesn't mean that if you get better grades, you'll get in less accidents. It just simply means in the long run, if we look at many, many cases of people that have good grades in school, then in the long run, again, it's not everybody. What is hard for us is we start to think about individual cases, and we'll say, well, my friend is number 1 in the class and they're a terrible driver. Well, that's fine, but we're not talking about that one particular person. We're talking about in the long run, when people tend to get higher grades, they're probably more careful. They pay attention to details in general, in the long run. Okay? Doesn't mean a situation with your friend or who you know. So we really have to try to move away from that kind of thinking to really be able to embrace and understand probability. And that's what insurance companies do. And they make lots of money, and they have lots of commercials on TV as a result. So that's what's happening here. They're saying, look, we're just going to charge everybody $750 because in the long run, we know that's going to make us money. They'll pay that, and we'll have to pay when something happens. If you have insurance and you can't get your phone fixed, they'll help you out, or get your car fixed, whatever the insurance is. But in the long run, the insurance companies win. They make monies. Okay. Next example we roll a die 12 times and record the result for each roll. Which of the following outcomes is more probable? 1, 2, 3, 4, 5, 6, 6, 5, 4, 3, 2, 1. 10 rolls. Or this one. So I think most people would look at this and go, gee, this is really, really unlikely. How could they possibly get 1, 2, 3, 4, 5, 6 in a row? Well, why would that be any more likely than this first round of numbers? They ought to be equally likely, right? Because just because there's a pattern in the numbers, it's random, right? If we roll the die, that can happen. But as humans, a lot of times we look at a situation like that and we think it's remarkable. And in truth, it's really not. We have these runs. If they're random, random is random. And now we're looking at this New York Times article, looking back at Joe DiMaggio's 56 consecutive game hitting streak. And, this is statisticians sort of, like putting sour milk in your cornflakes, I suppose. But, it's still extremely impressive that, a baseball player would go on a streak like that. But so what they did, though, is they simulated this many, many times. And they're saying, well, in the course of this many seasons, right, it doesn't take away from the achievement. But what it suggests is that in the course of that many seasons, if we're going to have this much baseball history, we should expect some exceptional things to happen. Should we still honor Joe DiMaggio for being the exceptional player who accomplished that? Absolutely. But what they're saying is, looking at it from a different perspective, is not like, don't think that this is impossible. Don't think that this, would never have happened. It's likely that somebody in the course of that many seasons, of that many games, is going to do something this impressive or this unusual. Okay. So in fact, they even, in their simulations, they found one that had 109, right? After, many, many trials. All right. So let's look at this example, and we're going to run the simulation, and I'll give you some questions to answer in the Edpuzzle. But we want to choose a simple random sample of 6. Right? So that's our goal to start with, of a group of 60 seniors and 30 juniors. Okay. So what do they do first? They put everybody's name on an equally sized piece of paper. Nothing wrong with that. And they mix them in a large grocery bag. Again, similar to the Pollyanna question that I'm presently working on. So just as about to select the name, a thoughtful student suggests that I should stratify by class. It's a good idea, right? Because it makes more sense that if we're going to take 6, a sample size of 6, that maybe we should represent this proportion, right? We should have twice as many seniors as we do juniors. So if we have a sample size of 6, think about it. Wouldn't it make sense to have 4 seniors and only 2 juniors? That would be the appropriate ratio, right? So we still have a sample size of 6, but we represent that proportion 2/3 to 1/3. So the teacher agrees, but now do we go back into the bag and figure out who the seniors are and the juniors are? That could take a while, okay? Instead, we're going to take the names one at a time until we get 4 seniors and 2 juniors, okay? So let's design and carry out a simulation using Table D. Let's use our calculator. Let's go with the calculator here instead, okay? So let's tell our calculator, okay, to give us numbers between 1 and 6. So we're going to say to the calculator, execute this command, random integer 1, 6, okay? And we're going to take and give us 6 numbers at a time. Now, what we are going to do behind the scenes is we are going to say, let any number that is 1 to 4 equal a senior. And repeats are okay. We're talking about a probability number here. So we're not meaning, the numbers 1 through 6 don't mean specific students. So if I get the number 1 twice, it's okay. It just means that I got 2 seniors, okay? The numbers 5 and 6 will represent juniors. So again, if I get the number 5 twice, that's okay. It means that I selected 2 juniors. We're doing a simulation here. There's a difference between a simulation and what we did in the last chapter where we were picking, like randomizing treatments or picking subjects. Okay, so I want to make sure that we're clear on that. So I'm going to execute this command, and what I need is I need 4 numbers that live between 1 and 4 and 2 numbers that live between 5 and 6. And that's it. Once that happens, okay, we'll look at how many trials it took us to do this. It's very similar to how I pursued the birthday problem the first time we looked at it. We'll just use a simulation. So I'm going to go to math and get myself to probability, and I'm going to use that random integer command. We're just going to keep on executing this over and over, even if you don't have a setup that looks like this. I'll show you what yours ought to look like. We want to select 6 students. Okay, so your setup should look like this: random integer 1, 6, 6, and I think I wrote that up here, right? We're just going to keep doing this until we get 4 juniors, 4 seniors and 2 juniors. So what happened in this situation here? Let's see, we got 3, 2, 3, 2, 2, 5. So what happened here? This looks like this is 1 junior and 4 seniors. So that's 5 seniors. Okay, so that's not a win. What we want, again, we want exactly 4 seniors and exactly 2 juniors, right? So what happened here, there's only 1 junior that I can see right here, number 5. The rest of these are seniors, right? So let's just do it again. Just press enter again on your calculator. It'll do it again. 4, 2, 3, 4, 4, 1. So what happened here? 5 seniors, right? We didn't get any juniors. So that's a no. Let's do it again. Just press enter on your calculator. 2, 3, 1, 6, 4, 5. Okay. So I think we got it now, right? Did we get senior, 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 senior? So we got 4 seniors and 2 juniors, and that is what we wanted. So if we were going to estimate this, we would say, we would have a 1 in 3 chance. Estimate the probability that you must draw 10 or more names or to get 4 seniors and 2 juniors. So we answered this a little bit differently. There's a 1 in 3 chance if we just take 6 at a time. 1/3, this would be our estimate. Okay, and this would be our estimate. Okay, it's not theoretical. To get the theoretical probability, that is a little bit more advanced, but selecting 6 at a time. Now, their question is saying we want to carry out a simulation to estimate the probability that you must draw 10 or more names until you get 4 juniors or 4 seniors and 2 juniors. So to answer that, the probability that we must draw 10 or more names, I would do that a little bit differently. Let me explain how I would look at that. I would use random integer 1, 6, 9, okay? And if I get my 4 juniors and 2 seniors in this situation, then I move on, right? And I'll just do this many, many times. So let's look at the first 9 numbers we get. So we have a senior, 2 juniors, senior, senior, junior, senior, right? So in our first trial, I'll just keep a running tab of it, number of trials, okay, and whether we had a success or a fail on that trial. All right. So in the very first trial, we were able to get 4 seniors and 2 juniors. So now I'm going to do it again. I'm just going to press enter. Do it again. So remember, 10 or more is just going to be 1 minus whatever probability we get here. So we have senior, senior, senior. There's 3 seniors. Here's a junior, senior, junior. Got it. That was another success. Okay. And then I would just continue to do this. Maybe I do this 10 times or 20 times or 100 times. And then I just look at how many times out of 10 trials or out of 20 trials did I get my four seniors and 2 juniors in less than 10, right? That's why I was doing 9 at a time. I look at 9 names at a time. And on my first 2 trials, I was successful. I got my 4 seniors and my 2 juniors. So it's a little bit different approach here, but I would continue to do that many, many times. And then I would look at how many times, out of 10 trials or out of 20 trials, did I get my 4 seniors and 2 juniors. It seems pretty likely. It's going to be really unlikely that you're going to need 10 or more trials, right? Here we have senior, junior, senior, senior. So I have my two juniors covered. Junior, junior, junior. So it seems like every time I do this with 9 people, I'm getting my juniors and seniors covered. So here I have more juniors than I need. I have 4 of them, but then the rest are all seniors. So I would just take the first 2 juniors I got, and then I get the first 4 seniors that I got. So far I have not been able to fail at this, right? Every time. So it seems, whatever our probability is going to estimate is going to be really, really close to 0 that it would take 10 or more names. Right? It's not going to take that many names to get exactly 4 seniors and 2 juniors. And what we would do though in that situation is the first 4 seniors are the ones picked. If we get more than 4 seniors, we ignore them. And then the first 2 juniors are the ones that are picked. Okay, so finally we have one more simulation. At their annual picnic, 18 students in the math statistics department at a university decide to play a softball game. 12 of the 18 are math majors and 6 are stats majors. So I'm just going to jot that down off to the side here. 12/18 is my math situation here, and 6/18 is my statistics situation. Majors. Okay. So it looks like 2/3 to 1/3. To divide it into 2 teams of 9, one of the professors put all the players' names into a hat. So we see what we're doing here again. It's like the Pollyanna situation. Out of 9 players to form 1 team. So with the remaining 9 players forming the other team, the players were surprised when one team was made up of entirely math majors. Is it possible that the names weren't adequately mixed in the hat, or could this have happened by chance? Right. So we want to say if this is the probability that we get math major, what's the probability that all 9 players are math majors? Okay. So we're going to do the same thing. I'm going to do random integer. Okay. And I want to simulate these 2 proportions. This is 2/3 and this is 1/3. Okay. So I'm going to tell the calculator, give me numbers between 1 and 3, and give me 9 of them. Okay. If I get a number that is a 1 or a 2, that's a math major. If I get the 3, that is a stats major. And then I'll do this many, many times. Okay. And I'll look at how many times out of 10 trials or out of 20 trials did we get all 9 players to be a 1 or a 2. That's what happens here. Okay. We pick 9 numbers and they're all 1s and 2s. So we go to math, probability, random integer. We start at 1, go to 3, and we're going to grab 9 players at a time. So if you don't have a calculator set up like that, it's going to look like this, 1, 3, 9. All right. So did I get all math majors? I did not. Okay. So on my first trial, that was a fail. Okay. And I'm going to do it again. Again, I want all 1s and 2s. It hasn't happened in 3 trials. So I'm just going to write failure. Okay. I need this to be all 1s and 2s in order for this phenomenon to happen. Almost. Another fail. Super close, right? But still not quite. We had 1, 3. Nope. How many trials I got? 1, 2, 3, 4, 5, 6. Let's do 4 more. Let's get 10. Nope. Nope. One more. Close. All right. But what we want to do is maybe do more than 10 trials, do 20. So if maybe out of 20 trials it happened once, right? If it happened once out of 20 trials, we'd say, well, there's about a 0.5 or 5% chance that would happen. My conclusion would be like probably to say they probably weren't adequately mixed. That's what that sounds like to me. If I just did 10 trials and not once did I get 9 math majors in my simulation, this does not seem like a phenomenon that is very likely to happen.